welcome to this fifth part in this mini-series on exponentials and logarithms at the higher level. And this will be the penultimate video in this mini-series. And here I'll be talking about what are sometimes called the Laws of Logarithms, and really explain to a large degree why they were introduced and why they are so important. Because essentially, as I hinted at in the last tutorial, they enabled very rapid calculation in an age back in the 1600s when calculations were done by hand and often were extremely lengthy. So, as we'll see, logarithms provide an amazing way to speed up these calculations. So, let me show you directly how this works, and I'll introduce to you the so-called laws of logarithms. And we'll just use a generic base A for these logarithms. These laws hold for any base. And the first law is the following, that if you have two logarithms to the same base, log little base little a of some number a plus log, again to the same base but of some other number b, then this can be written as a single logarithm of the product. So we're essentially concatenating two logarithms into one, and we're essentially saying that the log of a number plus log of a different number is the same as the log of the product. The second law of logarithms is very similar actually to the first. It simply says that log to the base a of some number and now minus log to the same base of some other number is the logarithm of the ratio or the quotient of those two numbers. All right. And before I list the third and final law of logarithms, I must point out a very important thing here, which is that these laws are only true if you see the sum of two logarithms written down. You can only combine them into one immediately if the coefficients of each logarithm are unity. If you have different coefficients, say I have log a plus 2 log b, I would not be able to directly use this law. So be very careful, particularly in exam questions. They like to test you on these laws, but you can only use these rules that I've written so far if the coefficients are the same before each logarithm. And the third and final law of logarithms that we'll be concerned with is the following, that if you have a number, let me just call the number p, multiplied by a logarithm, then you can absorb that number into the logarithm by writing it as logarithm to the base little a of whatever number you have raised to the power of p. So let me just give you some examples to make this seem much more sort of clear. I'll just choose some arbitrary base. Let me say choose base 10, because that's quite a commonly used base. So it's just an example. These laws hold for any base, so I'm just choosing this for concreteness. So that first one, then I could write something like log to the base 10 of 7 plus log to the base 10 of 2 is equal to log to the base 10 of the product, 7 times 2, which of course equals log to the base 10 of 14. Okay. And an example of the second law of logarithms would be something like log to the base 10 of, say, 24 minus log to the base 10 of 8. I can write this as the quotient within one single logarithm. And you see this simplifies down very nicely to log to the base 10 of 3. An example of the third law there would be something like if I have 2 log to the base 10 of, say, 5, I could write that as log to the base 10 of 5 squared, which would be log to the base 10 of 25. So these are the 3 laws of logarithms, and here are some examples. Remember, they hold for any base, and what examiners enjoy doing is really testing your knowledge of manipulating logarithms using these 3 laws. Something to bear in mind here is sometimes you'll want to go backwards with this third law, and you'll notice that what you'd need to do is to see, is the thing that I'm taking the logarithm of expressible as a power? So, for example, if I go backwards, I could write something like log to the base 10 of, for example, of 8. I could recognize that, well, that's actually can be written as log to the base 10 of 2 to the power of 3. And that 3 can then come outside. And so log to the base 10 of 8 is equivalent to 3 times log to the base 10 of 2. And we can see that connection because we recognize that 8 can be expressed as a number to a power. Okay. An important thing to recognize when you're doing these kinds of manipulations is the following thing. Because we know that a fundamental property of logarithms is that log to the base a of the base itself is 1, this means that we can express any number actually in the following way. We could choose to express a number n, say, as n times 1, and then write the 1 as log to the base log to the base a of a, and then absorb that n into the logarithm. So this would be log to the base a of a to the n. So this is an important special case of the third law to always be kind of alert to, that if the number that you're taking a logarithm of can be expressed as the base to a power, then actually it's equal to that very power itself, because you'll bring the power outside, you'll then be left with log to the base a of a, and that as a fundamental property of logarithms is just unity. So for example, let me do an example here. Let's say log to the base 8 of 64. I can write as log to the base 8 of 8 squared. I can bring the 2 outside, so this would be 2 log to the base 8 of 8, but then log to the base a of a is always 1, so log to the base 8 of 8 is 1, and so this number is actually just 2. So again, good to be quite alert to that kind of thing. I have actually to hand an example from an exam. Let me just show you. This is from, I think this might be from the 2019 Scottish higher maths paper, but the student was asked to simplify the following expression. Log to the base 10 of 4 plus 2 log to the base 10 of 5. And this is quite a nice example because it uses many of the things that we've spoken about. So the first thing to recognize is that we can't directly concatenate these into a single logarithm because we have different coefficients before the two logarithms. So in order to implement this concatenation in the first law, we have to get rid of this 2 here, and we can do that by just absorbing it into the logarithm. So we can write this as log to the base 10 of 4 plus log to the base 10 of 5 squared. All right. We can then implement the first law of logarithms and bring these together. So this would be a single logarithm of the product 4 times 5 squared. Now 5 squared is 25, so 4 times 25 is 100. And you might be content to leave it at that, but actually a final mark would be awarded for recognizing that this is a case of what we spoke about above, where the thing we're taking a logarithm of is actually easily expressed as the base to a power. So the final step would be to recognize that we can write 100 as 10 squared. We can then take that 2 outside, and we're left with log to the base 10 of 10. That's just 1, and so finally then we have the number 2. So this is actually quite a satisfying sort of game, really, that by playing around with these laws of logarithms, you can, take quite complicated looking expressions and simplify them into something drastically simpler, in this case just an integer 2. Why were these so important, hundreds of years ago in doing calculations, and who was doing those calculations? Well, the main people doing hard calculations were astronomers, because they were using quite complicated mathematics to predict the orbits of planets and comets and so forth, and would often spend weeks on end doing lengthy calculations. Of course, the issue is doing lengthy calculations that one tiny slip will ruin the rest of the calculation. So no matter how much you check, we're only human, and humans are fallible, and so errors will inevitably creep in. These amazing, I think they were regarded as miraculous when they were first introduced by John Napier, because you see what you're essentially doing is taking multiplication, a product, and expressing it as addition. And as we all know, addition is much simpler than multiplication. Similarly, we're taking division and replacing it by subtraction. And we're taking powers and replacing that by multiplication. So huge simplification. And the only trick is you just need to know what these logarithms are. And so people created what are called logarithm tables, where they would list, say, the logarithms of, say, the first 1,000 integers, and the reverse of those logarithms, which of course essentially are the exponentials, they were called anti-logarithms. And therefore, if you had, say, some complicated calculation, you needed to multiply two very large numbers together, what you could do is essentially say, well, the logarithm of that would just be the sum of the logarithms of the individual numbers. You would look up in your log tables what the log of those two numbers is, perform that addition, and then look in the log tables what number has that value, and then take the anti-logarithm, and that would give you the product. And you could do the same with division or with powers. So suddenly you had this remarkably rapid way of doing calculations accurately. I think there's some quote from those days in the early 1600s that said, the wonderful laws of logarithms, double the lifetime of astronomers, because they could do twice as many calculations in the same time, and also actually probably save them from despair as well, because the chance of error was massively decreased. Before we end here, let me just indicate where these laws come from, because there's nothing mysterious about them, even though they look maybe possibly mysterious. But let's see where they come from. Let me derive the first of these, and you'll see it'll be very straightforward to derive the others. The key point is, remember, because the logarithm is the inverse function of an exponential, we have these expressions which we talked about in the previous tutorial. So the function of an inverse just gives you back the argument of the inverse function, and so we would have that the exponential of a logarithm of something, let's just call it x, gives you back x. In other words, the function of its own inverse just returns the original subject of the functions. So we could write something like the following. We could say some number capital A, I'm free to write that as an arbitrary number, an arbitrary base little a, raised to the power of the logarithm of that number. And I can do the same for some other number b. I can write b as little a log to the power of log base a of that number b. So these are essentially identities, but I'm also able to do that for the product. I can just say the product AB is the base raised to the power of log to the base a of that product. So I have an expression for the product in terms of a to the log of the product, but I can also form the product explicitly from these expressions. So I can also write that a times b is the expression I have for a multiplied by the expression I have for b. Oh, I'm writing base 10 there. I want just arbitrary base a. Okay, so a times b is just this expression for a times this expression for b. And then remember from National 5 Maths that when you have some number to a power multiplied by the same number to a different power, we know manipulating indices, we can write this as that number raised to the sum of the indices, or the sum of the powers. So this last step is just something from National 5 Maths, where when you multiply a to a power by a to a power, you can just add the powers together. And now we recognize then we have two expressions for the same thing. We have one expression for AB, another expression for AB. They're both base little a to a power, and so these powers must be the same. And this allows us to equate log of AB to log of A plus log of B. So that's a derivation of the first law of logarithms there, and by manipulating indices we'd very quickly be able to derive these other two. So that's a quick tutorial then on the laws of logarithms with some examples, and also giving you a sense of how you would derive them. They sort of transformed calculation back in the early 1600s, so there's fascinating history around logarithms which you might be interested in reading about. So I hope that's helpful. There's just one tutorial left in this mini-series on exponentials and logarithms, which is just to show you how you can use logarithms also to simplify the representation of data if you have powers or exponentials underlying the data. It's an incredibly useful tool in science. It's used all the time, all around the world, every day in scientific analysis. So we'll just be talking about that briefly, and that will then conclude the topic. So I hope you found that helpful, and I look forward to seeing you next time.